accepted.
Hello, everybody. How are you doing? Good. Cool. Welcome to the session Java 4 to 21, Kotlin, code coverage, and the best friend bytecode. We're going to have a little bit of scandals here, some intrigues, and investigations. My name is Evgeny Mandrikov, and I work in a such great company as SonarSource. You might have heard of us. Maybe you are using our products, SonarCube, SonarLint, SonarCloud. Nevertheless, company is great, but they can only dream that they own my opinions. What you're going to see today is not at all connected to this company. It's my opinions, my personal investigations based on a work which I do in a spare time. I do work on a JCOCO library, Java Code Coverage Library. So before we proceed, let me first check who is using SonarSource products. Oh, wonderful. And I guess you're also using JCOCO. Wonderful combination, right? OK, let's move on. While developing JCOCO, we do test it on 16, as of today, if I'm not mistaken, and a half GDK versions. Why half? Because we're also testing it on early access builds of GDKs which are not yet released, like GDK 21 is not yet released, but we're already testing it. Sometimes we do find bugs in GDK. Quite some time ago, I don't know if it still holds, but some time ago, we was actually one of the top contributors to the GDK bugs. Why so, and what kind of bugs? Maybe we're going to see together with you, maybe not. We'll see. Sometimes, of course, we implement new features. For example, report generated by JCOCO version 0.8.1 for some Kotlin classes quite some time ago looked like this. You might see that, and you might think that there is quite some uncovered code for which you need to write tests. And we work it a little bit, and without modification of those Kotlin classes, report started to look differently. It now says 100% coverage. Why so? What we did is exactly what we're going to see today. Before we proceed, it's important to understand that JCOCO receives all the information from the class files. Source files do not play much role in the process of collecting and actually computing code coverage. Everything is stored in already compiled class files. What do you see in the report is happening just at the end. We are going to see how we link class files to the source files that are shown to you, but this does not participate in the process of calculation. Everything what JCOCO does is done by looking inside of the class files, into the bytecode. And that's about what we are going to talk today. So there is a nice properties out of this requirement to look only on the class files. We don't need to implement instrumentation of the source code. We can implement instrumentation of the bytecode, and to gather the code coverage, you just need to attach Java agent to the application at the start, and you're going to get all the data. Absence of source files is not a problem. In this case, you can measure code coverage even of some library for which you lost the source code. You can take it, you can execute some use cases, and you're going to see which classes you touched. And this opens a door it simplifies support of a new syntactic sugar, like text blocks appeared in GDK 15. It's just a syntactic sugar. It doesn't change the bytecode, so we don't need to do anything. If we would have to implement the code coverage tool based on the source code, we would have to adapt to such source code changes. And, well, for other syntactic sugar, which might come later in new GDK versions, like concise method bodies or whatever else is going to come tomorrow. Also, we thought that this will help us to actually have one implementation, one library for other JVM languages, like Kotlin. Why we thought, why I'm not so sure anymore nowadays, we're going to see today. It mostly works for other languages, but there is some troubles, and I'm going to show you those troubles. And now here is a real disclaimer. Sorry for this, but there will be a little bit blood out of JVM. Sorry for this, we're going to look on the naked Kotlin compiler and Java compiler. We're not going to use IDE or whatever. We're going to use the command line to execute compilers. Sorry for this, we're not going to speak even English. We're going to speak strong language bytecode. And sorry for this, I'm going to do I will try to do intense violence of your brain. If you're not ready for this, doors are still open. If you all leave, maybe I will attend another wonderful session. So, are you ready? You seem to be sleepy. But lunch was 1 hour ago. So, okay, let's warm up. We need to warm up a little bit, so I will be increasing complexity and maybe speed so that you can wake up. Let's start from something very simple, very basic. Empty class. With the name bless me. Class bless me, 2 curly braces. Simple, right? Who agrees that this class is empty? There is nothing inside. Okay, wake up. Oh, you're already waking up. Wonderful. Indeed, if we're going to compile this class bless me, if we're going to decompile it, and that's what we will be doing today. We're going to use the decompiler. The basic decompiler comes with GDK. It's presented on every machine where GDK is presented. It's called Java P. And there is 2 wonderful options, -v verbose and -p private, protected, etc. I call those 2 options basically show me everything. Java P, -v, -p, it's going to show me everything what is inside of class file. If you're going to look at the compiled class file, we're going to see when it was created, its checksum, from which source file it was compiled. We're going to see the Java version. In this case, it was compiled using GDK8 for GDK8, so we're going to see major version 52 in the bytecode. We're going to see some constants which are declared in this class file. This is the first, and I hope the last time you see the constant pool. I'm going to be omitting this on the next slides. And we're going to see the actual content, the methods in this class. And indeed, holy place can't be empty. We see the default constructor, which is generated by the compiler for us. What will, yes, constructor. Why we are going to see the constructor? Because there is a requirement. Every object in Java inherits from some other object. In particular, if you do not declare from what you inherit from the Java-lang object. And we need to call a super constructor of our super object. So that's why compiler generates the default method. And well, there is some return. And here is the link with the source. The only link with the source code in the bytecode, in the compiled class files, is 2 things. So-called line number table, which says basically line number 1 associated with the bytecode instruction at this offset. In this particular case, line number 1 associated with the bytecode instruction 0, so everything what follows bytecode instruction after offset 0 corresponds to line number 1. And another link is a source file name. Notice that there is no package name. It's always going to be just the source file name. And it's not a path on the disk. It's just a name. Let's complexify a little bit our example. Let's do something more complex than empty, because empty was too easy for you. We have an outer class. We have an inner class declared in this outer class. And we have a private constructor in the inner class. And we do construct inner class outside of it, inside of the outer in some method. So if we compile this, what's going to happen? Do you know? Sorry? Yes, there will be 2 files, one for outer, one for inner. That's kind of obvious. What else is going to happen? Well, we already answered one question, whether this is allowed or not, whether this compiles or not. Yes, it compiles. But okay, let's don't guess, let's just have a look. Java p minus v minus p outer. What we're going to see in outer? Again, I used my favorite Java, Java 8. It contains major version 52. Here is our method, which contains constructor invocation. But what we could notice is that constructor has one argument. Our constructor was not requiring any argument. And here we pass null to this constructor. What the fuck? Let's have a look at the inner class. What happens in the inner class? There is a private constructor. This constructor we declared in our source code. Here is constructor with a parameter. Okay, and the parameter type is one more class. So, and by the way, it's package local, not anymore private. We also could notice that it contains a special attribute synthetic. About synthetic, we're going to see a little bit later. Just remember this. It's package local. And it just delegates to invocation of our private constructor. If we're going to have a look at one more generated class, by the way, we were wrong here. There is going to be not two classes. There are going to be 3 generated classes. And we could notice that this time, this generated class is truly empty. There is no constructor and superconstructor invocation. There is no way to construct instance of this class. Why so? And it's also synthetic, market synthetic, etc. Why so? The reason for this is there was misalignment between Java language specification and Java virtual machine specification. Java language specification allows you to access privates of one class from the other as long as they reside in the same source file. It's okay. But from the Java virtual machine specification, it's not okay. Those two classes are separate classes. They reside not in the same file. They reside side by side, one to each other. And one cannot access privates of the other. How to solve this misalignment? A long, long time ago, the decision was made to solve this misalignment by a compiler trick. Compiler under the hood could generate this package local constructor that allows to overcome the restriction of JVM and let you call the private constructor. Let JVM believe that it's okay to call the private constructor. Thankfully, Java evolves nowadays quite rapidly, and there is some space to clean up this mess. So there was JEP 181, nest-based access control, implemented in Java 11. If we're going to compile exactly the same source code, but using JDK 11 or above, we're going to see slightly different story. Major version is 55, Java 11. There is significant weight loss. There is no need anymore to generate this package local constructor. Your classes just got smaller. And why it is possible? Because there is a new attribute, nest host. This attribute allows JVM to verify that indeed outer class should have access to this inner class. They are connected together. But let's move on. Let's have a look on the other example. What do we have here? We have two classes. One extends another one. And we have two methods. One overrides another one. The only difference is that they have two different return types. One returns object, another returns string. What's going to happen if we compile this? First of all, can we write source code like this? No? Who thinks no? Okay. Sorry, but we can do like this. And I would be surprised if we could not. But OK. Let's see what is going to happen inside. We again compile, we again decompile, and look. This time we're going to use Java 18, major version 62, just to be sure that we got all this nest-based access control, etc., all the improvements, blah, blah, blah. We're going to see our fun method, which we wrote. It contains return type javalang string. It just returns now. Bam. We're going to see another fun method. We didn't write this one. And it's again synthetic. Moreover, it contains one more attribute, bridge. This, again, another JVM trick or Java compiler trick in order to, indeed, bridge things together. Why this is allowed? To override one method by the other and change the return type. Because, well, all the places where a base class, the superclass, is accepted should accept a child as well. But all the base classes, when they invoke methods, they do expect certain signature and certain return type. In particular, when they invoke fun method that is declared in base, they do expect that result is the object, not the string. So in order to allow passing the child to those methods, compiler have to generate so-called synthetic bridge, which returns object. And this synthetic bridge does a simple, stupid thing. It just delegates to original methods. That's it. And now time has come to learn about this synthetic attribute. What this synthetic attribute is? Java virtual machine specification helps us. It says a class member that does not appear in the source code must be marked using synthetic attribute. And well, there is some exceptions. As usual, in every language, there is exceptions to every rule. And the only exceptions here is instance initialization method, default constructor, we saw it, class or interface initialization method, implicitly declared members of enum and record classes. For enums, you probably can guess every enum has a method value of and values. They are not marked as synthetic. Why they are not marked as synthetic? Why those exceptions? Well, the reason is whatever compiler generates, you should not be able to use. Only compiler can call those methods. You cannot write the source code that calls, for example, this bridge method. It should be hidden from you. Unfortunately, they cannot say, well, don't call values of method on the enums. This should be accessible to you. So even though it is automatically generated, it cannot be marked with a synthetic attribute because it should be accessible. So logical conclusion out of what we just learned is, well, if something is presented in the byte code, but not presented in the source code, and Jacoco operates on the byte code, but should show you the source code, the logical conclusion, we should ignore synthetic methods. Otherwise, you would see them in your code coverage reports, and you will be wondering what this is. And I never wrote this method, why I need to invoke it. Maybe you never invoke it, and etc. This does not matter to you because it's after-generated code. Let's trust the generator. Java compiler does a good job here, the right one. We need to test not the generated code, but the generator. And well, OpenJDK developers, they test the Java compiler. Right? Is there any problems with this? Let's have a look. Lambdas. Simple example. We have a method exec, it accepts renable, it calls it invokes this renable. We have method fun. It invokes method exec, and it passes lambda. And inside of this lambda, we have system out printer and joker. What we do expect when we do compile this? We expect to see joker inside of a method fun, right? It's just there. Let's try. There's an argument. We compile with the compiler. Here is a method exec. Do you see joker? I don't. But we are looking on the wrong method, right? We should be looking on method fun. Here is method fun. Do you see joker now? I don't. Why? If you know what is behind lambdas, lambdas are not just a syntactic sugar. Behind lambdas, there is a heavy machinery, call it invoke dynamic. There is no joker, and even line 9 disappeared. What is in there is, you could see, there is invoke dynamic instruction. Invoke dynamic instruction associates this invoke dynamic instruction at the runtime is going to be associated with the actual object representing lambda, which is going to be constructed at runtime. And to do so, the body of lambda actually, by compiler, migrated into other method declared in your class. And this method is generated. Again, you should not be able to call it directly. It's mechanics of lambdas. It's internals of lambdas. As such, it is marked as synthetic. And here is our jacker. And here is our line number 9. So if we decide to ignore synthetic methods, we are going to ignore all lambdas. There is no coverage shown for lambdas in version 071 when lambdas just appeared. So what to do for our wonderful code coverage library? Well, we have to ignore all the synthetic methods except what? This implementation details how lambdas are implemented. Today, the current strategy of translating lambdas by Java compiler is to always prefix them with lambda $. And that's exactly what we did. If method is synthetic but starts with lambda $, it should be lambda. This works. But be careful, this is implementation details. This is not specified. And compilers do not need to obey this. Kotlin compiler does differently, Scala compiler does differently, Groovy compiler does differently. We developers of Jacko library have to adapt for this. Bam. Well, you might ask, do I have something non-synthetic or something other interesting examples? Fortunately or unfortunately, I don't. But inside of Java compilers, there is a lot of tricky places. Let's look more. Finally, do you know this construction, try finally? Pretty simple one. We try something, and no matter what, finally should be executed. So what do we have here? We have two methods. One method, as usual, fun, which contains try finally. We call another method nop 2 times, once in a try, once in a finally. Simple. What we expect to see in the compiled code, let's have a look. Somehow, I normally would expect to see just 2 invocations of method nop. But in the bytecode, we get 3. Or did we actually have 3 nops here? Let's count. 1, 2, 3. Right? But the third one is method declaration. We couldn't see invocation of it, right? Let me help you a little bit. Let's investigate. In order to understand which invocation which, let's add a marker, just a string. We're going to pass different strings inside of try body and inside of finally body. Let's have a look what we get inside. We get 1 try and 2 finally. Why so? Well, the reason is how try finally is implemented again by compiler in the bytecode. There is no such construction as try finally in the bytecode. In the bytecode, there is so-called exception table. Exception table says, if exception happened from this bytecode offset instruction to this one, then go to this offset and execute what is there. But we do know that finally blocks should be executed not only in case of exceptions, but also during normal flow of execution when exception is not thrown. So compiler has to, in case of exception, we will call the handler. Here is exception handler. And in case of absence of exception, we have to duplicate the body of finally to execute it. This is pretty interesting because compiler starts to duplicate finally blocks. So what you could try at home is to nest many try finally inside of each other. They're going to go exponentially. And sooner or later, you're going to reach a GVM limit on the method size. You could figure out how many nested try finally you could have in your program. This number is pretty small. So why is this again problem for us? Because people do not expect that finally is duplicated. People do not expect that they have to verify both cases. And sometimes it's even not possible to trigger certain branches in the finally because code just gets duplicated. You might have branches here which only happen on normal execution path and never happen on the exceptional execution path. So all of this needs to be filtered out. So what we implement in Jacoco is special filters that look into the bytecode pattern and try to detect the duplication of finally and to merge them together. So we get a wonderful report where you need to test just one of those flows. Either you got exceptional, you executed exceptional flow, or not exceptional. A little bit of archaeology. This actually was not implemented like this a long, long time ago in Java 1.4. In Java 1.4, there was a difference. There was indeed just two invocations because Java 1.4 exception handler, it was possible to implement using so-called Java subroutine instruction. It's a little subroutine, it's a little function inside of your function that you can call and from which you can return. Wonderful. But unfortunately, everything evolves. If you're interested why they got rid of this subroutine, you can refer to another wonderful presentation of my friend Nikita Lipsky, Java bytecode verification, when, how, or maybe to turn it off. But let's move on. More complex examples, and we don't have that much time left. Try with resources. We are moving from Java 1.4 to more recent days. When try with resources appeared? Right, Java 7. So in Java 7, we can declare some resource. We can say that it implements closable, so we get close method. And what is even more important, now we don't need to write try, catch, finally, and handle the exceptions. Try with resources is going to close this method once the resource is no more needed at the end of this try with resources block. Wonderful. What is behind try with resources? Do you know? Let's have a look. We don't need to guess. We now know that we can invoke Java p minus v minus p example. There is a lot of code. Can you see it? No, I can zoom in. There is 4 invocations of methods close on our resource. Why 4? Just to be sure that we close the resource no matter what. Let's call close 4 times, right? No, probably not. There is some branches. We check if something is null or not null. In order to help us to understand why it happens like it happens, there is actually a Java language specification which gives us an answer on this question. The meaning of a basic try with resources statement, and there is example of such try with resources statement, is given by the following translation to a local variable declaration and try catch finally statement. Try with resources is just a syntactic sugar over our good old friend try catch finally. And we just learned about finally that it gets duplicated on various execution flows. So that's why we get many clause. So, and what Java language specification provides as an example is this beast. This is how try with resources that you just seen looks while compiled. It's quite of a beast, right? Nobody probably would be able to write such code by hand, and that's why they introduced try with resources. It's hard to handle resources. Well, and what is interesting is that compilation of this source code is equivalent to the compilation of the source code with try with resources. We're going to get exactly the same bytecode at the end. You might say, no, you're kidding. It's not possible. We wrote 2 different source files. They should result in 2 different bytecodes. Can I prove it? Let's try. Maybe I can. Oop. So what do I have here? I have fun1, try with resources. I have fun2. This contains a crazy beast that you've just seen. We can even do what? Div fun1, fun2. Yeah. They're different. It's 2 different source files. Let me use what? You say it, Java 7 try with resources appeared. Let's compile fun1, and let's decompile it. And let's save result of compilation in 1.txt. Let's compile fun2. Let's decompile it, and let's save it in 2.txt. Let's do the diff. What we can see, they indeed slightly different. They were compiled from 2 different source files, fun1 and fun2. And yes, they're slightly different. They contain different line numbers. If we would write everything in the single line, even the line numbers would be the same. The rest of bytecode is exactly the same. Why this is interesting? This is again interesting for Java code coverage library because we again need to hide all this complexity from your reports. In your reports, you probably don't want to see which branches you covered in this crazy code. So indeed, we write special filters that matches this code, that tries to find this code, and filters it out. But now what happens? If you would ever write your source code like this, we will filter it out. We will say there is no source code. It's OK. It's OK because probably nobody would write this. But again, this is one of the difficulties that we face while implementing this library. So let's look what is in there. There is try catch, there is finally. In case of exception, we have to close the resource. If while closing the resource we got another exception, we should attach one to the other. In absence of exception, we just close the resource and let exception propagate. Bam! There is some null checks. These translation in Java-C always checks whether resource is null or not null. And if you just constructed the resource in your try with the resources statement, you know in advance that it cannot be null. The null check is useless. There is a dead code in this. That's why we need also to implement filter and filter this dead code. There is another dead code. This check verifies if we had an exception or not. And we know in advance that we got an exception only on exceptional pass, but not on a normal pass. So again, while duplicating finally, we can remove this null check. It's not needed on one of those passes. Bam. We gave this feedback to OpenJDK developers, and indeed, in Java version 8, there were some improvements. Instead of 4 null checks, we got 2. One of them was eliminated. Again, we reported this. If we are going to use Java C11, but still compile into Java 8 bytecode, we are going to see 0 null checks, because all of them can be eliminated. Nice. And together with all those improvements, we have to tune our filters, adapt to every new strategy that Java compiler takes to be able to find them. But this helps for you, for our users, to see a wonderful report that says, don't worry, there is no dead code inside. Don't worry, there is no branches inside. Bam. I hope you now warm it up and we can switch from Java to Kotlin. By the way, who is using Kotlin? Is there? Yeah, okay, quite some people. For those who are using, hopefully it will be interesting. For those who are not, I hope too. Kotlin got data classes. Kotlin got data classes far before Java got records. What's wonderful about data classes? Well, if you're going to look into the data classes, they do have some fields, obviously. Kotlin generates fast getters. Very synthetic. Well, again, remember, they cannot be marketed as synthetic. You should be able to use those getters, even though they are generated. So no synthetic. But it would be probably nice to find them and filter out, right? There is also setter, there is also constructor, which got generated. There is wonderful toString methods that you don't need to write. This needs to be filtered out. And again, the strategy to filter and find this out heavily depends on the translation strategy of compiler. Thankfully, guys from JetBrains helped us to understand strategy here. Certain generated method in Kotlin compiler, they do not have line numbers. We can filter them because they don't have line numbers, equals, etc. certain methods have, but others don't. So that's what we implemented. That's how the report improves. Well, thankfully, back to Java. In Java, we also got kind of data classes. We got records. You might guess what is inside. We zoom. Yes, there is fields. There is constructor. We got the generated toString. Can you notice something different compared to Kotlin? The same filtering strategy does not work. Java compiler decides to generate line numbers always. What we have to do? Well, we have to implement another strategy. We look inside of the toString method. If it uses a special invoke dynamic construction, we know that it's toString inside of records. But OK, we filter it out. We need to adapt, etc. Let's have a look on something more complicated. Java has, again, nowadays features the same as Kotlin. When on string or in Java, switch by string. So here's how it looks in Kotlin. We say, OK, if the string is A, then return 1. If the string is B, return 2. Otherwise, return 3. Simple. What we expect to see in the bytecode is probably these three cases, right? Let's have a look. We compile, we decompile. Here is a switch. How many cases we expected? 3, right? The default and 2 strings. But we got default and a number. Why so? Well, because in JVM, there is no switch by string. In JVM, there is switch by integer. One of the ways to implement switch by string is to do the series of if something equals to something, then else, if something equals to something else, then. This is inefficient. This is slow. The better strategy is to first do switch by hashcode. With high probability, all the strings that we list, they're going to have a different hashcode. So with a high probability, we would already choose the right case that we need. But in a rare case of hash collisions, we still need to do string equals. And that's exactly what happens in this example. Those 2 strings, B and AA, they happen to have exactly the same hashcode. And, well, there is a default case. Why this matters? Well, because in this code, there is not 3 branches as you would expect. There is one switch with 2 branches, and then 2 ifs with 2 branches each. So there is 6 branches. But you, in the source code, you do expect to see just 3 branches. So again, we have to implement filter for this, filter this out, etc., for you to get a perfect, wonderful reports with 100% coverage. Fun fact, even developers of IDE, JetBrains, who happened to be the developers of their own language, Kotlin, they cannot bridge those 2 worlds. They cannot implement the own code coverage tool or the compiler in a way that code coverage tool is not going to report those branches that you've never wrote. Bam. Let's move forward. What do we else have here? In Java 12, we got JEP 325. We got switch expressions. What is wonderful with them is that instead of writing the default case when we list all the possible values of enumerations, compiler is going to generate default for us, which simply throws incompatible class change error. Why compiler have to do this? Well, because of a split compilation. If it happened that you changed your enum after you compiled your switch, we need to execute some code and notify you that, well, the enum expected here is not the one that was expected here at the compilation. So the method cannot just do nothing. It should signal this error. That's why compiler generates incompatible class change error. In Java 14, we got another JEP 305, pattern matching for instance of. We can now write if some object is instance of string, then inside of this if we could use this string without casts, etc., etc. If we again compile this, here is it. how it was in Java 14 preview, we are going to see condition, which is OK, right? We had if, there is if. We're going to see another condition. But we had just one. What's that? Well, apparently, this is how instance of pattern matching was implemented. It was a syntactic sugar on top of well-known construction. We can place actually assignments inside of conditions. That's the way to do it. This introduces additional branches, which users do not expect. Moreover, this is a dead code because there is no way to evaluate this branch as false. It's always going to be true. People do not expect to see this in code coverage report, so we have to filter this out. Also, we reported this as inefficient compilation to Java C developers. This is a bug that I promised you we would find today. And, well, they got fixed it in Java 16. If we compile the same, we are going to see only one condition. We got more. In Java 17, we got pattern matching for switch. This time, well, Java 17. This time, all good. This switch is backed by another switch. Here is condition of the first case, body of the first case. If there is no match, there is special machinery to restart matching from the next point, which contains more conditions, etc. It's all good. There is invoke dynamic again, another use of the same construction that was used for lambdas before. The only problem with this code is that what quite often happens in Java compiler, they forget to take care of line number table. The line number table here is crazy. If you would take this Java compiler version, compile this example, and will try to step by step in the debugger through this code, the debugger will be jumping to some strange lines which are not actually executed. Again, we reported this. In fact, this time we even tested before it got merged, so there is no bug record. We just came to the pull request that was implementing the pattern matching, and we say it here. Well, we tested feature before you finished its implementation, but there is a problem. Could you please fix it? And well, they fix it. And we come now to the hard part. Hopefully, we have time for it. I hope you warm it up enough to understand what is going to be happening now. Kotlin. Do you know suspending functions? Coroutines in Kotlin. The ones who use Kotlin. Do you like coroutines? No? You don't like them? OK, the others don't use them. But OK, coroutines in a nice way to write concurrent code. You write it as like any other code. There is no synchronization, nothing. You write it in a normal, understandable way. There is some suspension points, and these suspension points, execution of your function might be suspended, and execution might be transferred to another operation, to another function. So those two are not blocking. While waiting the result of one, you can execute something else. Wonderful paradigm. In order to do this, unfortunately, there is much more to do in the compiler. These suspending functions and suspending points are a beast if you look in the bytecode. What is in there? Our simple small method with just a few 5 lines of code becomes such a beast that you cannot see it. Let me zoom in. It got a different signature. It was just one method that attempts int. Now it got additional argument, which is coroutine continuation. So here's a new parameter. It got this parameter of a new type. This new type was generated. This new class contains some fields. This new class contains some invoke suspended method. This original class contains some initialization of this class. Here is a suspension point. Suspension points are implemented as a table switch. Every time before suspension point, we have to, and after suspension point, after we have to restore the state of local variables, before we have to save state of local variables. Here is a save, restore, arguments, etc. Parameters. Suspension point contains additional checks. If we don't need to suspend, we can just continue execution. So there are some branches, again, which you didn't write. And this beast is quite hard to match for us. It's quite hard to implement patterns that would find this thing. But we need to do it, because what you as a user expect looking on code coverage report, you don't expect branches here at all. This is a linear execution. We just call some methods, assign some values to some variables. That's it. We don't expect switches, we don't expect comparisons, etc. Bam. Let's move on. Another beast, which we did not yet solve, Kotlin has inline functions. Thankfully, Java does not. I am really thankful to Java developers that we do not have inline functions. Inline functions give us a lot of troubles when dealing with Kotlin. For you, probably it's good. I don't know for what, but for us, it's a nightmare. Why? We have such inline function. There is one if condition. There is two branches. In those two branches, I print in one branch true, in another false. And I have a call side. This call side calls this inline function 2 times. Once I pass Boolean true, another one I pass Boolean false. What is going to happen if we compile this? Well, here is a call side. Here is a first copy of inline function. Inline functions literally copied to the call side. Here is a second copy. All good, except the first copy contains a constant string true, but not false. The second copy contains string false, but not true. So there is optimizer, which can strip some code out while copying. And for us, it's extremely hard to understand how this new inlined code looked before it was copied. Because in between us, there is optimizer. This is an unsolvable task, actually. Actually, the original task that I already showed to you, whether two programs, two source code are equivalent or not, is unsolvable. It's proven that it's unsolvable. It boils down to the halting problem.
What about the line code table?
Yes, they have. There is a line table, and this line table contains, for inlined parts, actually the numbers, the line numbers of the inlined parts. They contain numbers which are bigger than the numbers that you had in source code. Why so? Because they have a special attribute, source debug extension. This is actually a standardized thing. It's debugging support in JVM for other languages. This attribute contains information which maps these big line numbers to the original line numbers. We can parse this. We can use this to map line numbers. So we can approximately figure out which line number was mapped on which. But unfortunately, Kotlin is so functional that people sometimes write a single if on the single line. We can map lines, it's okay. But we cannot map branches. We don't know from this line which branch was aligned into which. This is one of the difficulties why we cannot solve this issue for you. Sorry. We are still thinking how to deal with this. We even talked with Kotlin compiler developers. They are puzzled the same way as we are. Conclusion. Source code is not bytecode. Be aware of this. Actually, what you write in the source code is not at all what is going to be executed by JVM. JVM executes bytecode. But even this is not true. Because there is just-in-time compiler. Just-in-time compiler is going to come and transform the bytecode into the native code. So JVM is going to execute native code. Processor is going to execute the native code. But be careful. Even this is not true. Because electrons pretend that they move. Why you should be aware of this? Bugs can be everywhere. bugs can be in Java compiler, as you've seen, bugs can be in JIT, bugs can be in Jacoco. Not everything what seems to you as bug in our code coverage library is actually bug in our code coverage library. We are absolutely honest with you. We are showing to you exactly what is in the bytecode. So, bytecode-based tools have to guess sometimes. Like with try with resources, there is no way to distinguish one from the other. Bytecode-based tools sometimes have no way to map things to each other. So, developers have to live with this. Please bear with us. Please understand that we cannot cover all those possible cases, etc. We try, but it's hard. And we, developers of such tools, when we deal with this, most of the time we receive angry users who come and say, oh, I was expecting my code coverage report to have 100%, and you are showing to me that there is, I don't know, 6 branches that we didn't cover it. They're very angry. They want these 6 branches to disappear. That's okay. We're going to figure out what those 6 branches, we are going to implement some filters, etc., etc. What we almost never receive from our users is when things work just fine as they expected. So if you can take just one thing out of this talk, please take this. Be thankful for open source developers, which do provide some tools for you for free in their spare time. Go to their mailing list, issue tracker, or whatever, and just say thank you. This will be really motivating for them to continue their work. Thank you for your attention.